Okay, so welcome to lecture 16, I think it is. Here I'm going to go on with limit cycles. I'm going to basically argue that there's no chaos in 2 dimensions, and then introduce Leonard systems. So we're now going to start looking at the systems that they established when they started developing the radio. This is where it comes from. So the system basically is a dynamical system that comes from a radio circuit and was involved with radio tuning. So firstly, the result that there's no chaos in 2D is basically a combination of the Poincare-Bendixson theorem that says there are limited possibilities in phase space. If you have an orbit that is trapped, okay, in other words, a closed trajectory in a bounded region with no fixed points, then the only possibility is it must approach a closed orbit and it must be a limit cycle. Okay. And it also is exclusive. It says nothing else is possible. And you can remember that picture that I showed you that follows from the uniqueness of the ODEs. The trajectories can't cross, and so there's basically, because you're in 2 dimensions, nowhere else to go, either to the limit cycle or to a fixed point. And if there are no fixed points in a trapped region, it will always go to the limit cycle. That's the only thing that's possible. But what that also does is it limits in 2 dimensions the possibilities. So in higher dimensions, remember the Poincare-Bendixson, you can't prove it does not apply. There are more complicated things in higher dimensions, and we'll look at some of them when we start looking at the Leonard attractor. Okay, and so in n higher, greater than or equals to 3, we can get chaos and can start looking at the properties. But it's just, I just wanted to record that the Poincare-Bendixson theorem is basically the proof that tells you there's no chaos in 2 dimensions, just because of the topology. Okay, so now I'm going to start looking at Leonard systems. And where this comes in is we've now gotten to the point where we can show a limit cycle exists. We can say where it is. And the aim in the next couple of lectures is actually to describe properties of this limit cycle. Okay, so we want to actually get analytic handles on the limit cycle, and what would you like to describe? Like a limit cycle is something that's periodic, what would you like to know about it? Maybe how big it is, and maybe the time it takes to go round, because that sets the frequency, and that sets like what frequency the radio would tune into, what frequency your heart would beat, right? Your heart can't beat at any rhythm. And there's a reason why most humans' heartbeat has a certain range. And that range is set by it having to pump liquid through your whole capillary system. And your veins and stuff have put a speed limit on that liquid. So your heart has to pump at the right frequency so that your liquid can circulate through. Okay, and in fact, that's what sets the heart rhythm that we have. It's a pump designed to be optimally associated with your body, right? Okay, so a Leonard system is a specialized system where we can actually say something about the amplitude and the period of the oscillation, even though the limit cycle has a really, really weird shape. So how it works, it's found in many oscillating circuits, which is why we're studying it. And it's basically, the part we're going to look at now is the mathematical formalization of what a whole bunch of people found when they were looking at radio circuits. So they were exploring with radio circuits. You had 2 ways of approaching. The one was you build a circuit and you try and make a circuit that can tune. Eventually you learn what you have to do in the circuit. And then the next step is you try and understand it enough that you can manipulate it. So, and Leonard systems are sort of the understanding of that. Okay. They also used it a lot in vacuum technology. So vacuum technology, the first televisions that were not flat screens had this vacuum tube at the back, and it was also used in there. Okay. And so all it is a differential equation that looks like this. Okay, so it's a linear in derivatives second order differential equation where you have functions f and g, and it's equals to 0. And these f and g have certain properties. Okay, so if we write it as a first order system, we can write it like that. And what we're going to do is look at the properties of f and g so that we can actually describe the solution that has a limit cycle. Okay, so Leonard Theorem is if you have this differential equation, okay, and he's a Russian, haha. Okay, so, well, this is actually also interesting, and look at the date, right? It was just after the Second World War. They were starting to write up all the discoveries they had made. Science started up after the Second World War, and they started publishing it in Russian. And there's always been this little bit of a the French wanted to publish in French, the Russians wanted to publish in Russia, the Brits and Americans wanted to publish in English, and there was like this fight. And so a lot of the literature, especially because the Russian school was so good, analytically strong, it was sort of self-contained. This is why, and they saw no need to help always to translate it into English. There just was no need because they had the information. So there were then, and that's also the reason why some of the Americans learned Russian, or the American scientists learned Russian to be able to read the literature. It's part of the reason I know a bit of German as well. It's because I wanted to know something. Okay, so the equation goes like, suppose f and g in Leonard's equation are continuously differentiable, so they're just ordinary functions that we expect. G has a symmetry, is antisymmetric. In other words, g of minus x is equals to minus g of x for all x. Okay, so it's an odd function. G is greater than 0 for x greater than 0. Okay. F is even, so f of minus x is equals to f of x for all x, so it's an even function. The integral of f from 0 to x is an odd function, okay, which is to be expected, right? Usually the integral of an even function is an odd function, provided you're starting at the right point. So those are the 5 conditions, okay, and then additional thing is it has a unique 0 at x equals to a. Okay, so it's got to have at least 1 0. And its derivative is greater than 0 for all x greater than a. And it is f of x is less than 0 if x is in between 0 and a. So do you know what this function looks like? Okay. Something like that, right? So you basically have this function, f of x is the little f of x is the function appearing in here. Then you have its integral. It's an even function. You have the integral, which is an odd function. And it has the property that it has a unique positive 0 at x equals to a over there. Its derivative and itself is positive in this region, so it's an increasing positive function for x greater than a. But between 0 and a, it is less than 0. And so, yeah, you have it. Okay. And the reason for all this nitpicking is basically it's the simplest possible system that you can say a lot about and that you can guarantee a limit cycle for. So the theorem now is that, or that Leonard proved, is that then the system has a unique stable limit cycle surrounding the origin in phase space. Okay, so it's a powerful theorem. It incorporates quite a number of systems because f of x can vary, but it is always true that it has a unique stable limit cycle that surrounds the origin in phase space. And we're going to explore these systems because they appear so often. So typically what Leonard did is look at all the radio data or the radio circuits, and he tried to find what was common in all of them, and this is what he came up with. Okay, so now let's have a look at it more carefully. Okay, so there's our Leonard system again, and let's try and prove what happens or how the limit cycle exists. And the nice thing about a Leonard system, it's sort of a constructive proof. So it's a very clever set of coordinate transformations that they applied to actually do the proof and to understand these systems. And these are basically due to Leonard. So his transformation is he wants a new variable, w of t, and it's a different type of transformation than what we've been looking at. We've written this as a first order system like I did on the previous slide, where we just said the new variable y is equals to x dot, and then you work out what y dot is. This is going to introduce a new way of writing the first order system. So we introduce this new variable, w of t, which is x dot, but it's not just x dot, it's x dot plus f of x of t. Okay, so we've included this integrated function of f of x, which is odd and has a 0 in this new variable. If you then go on and you work out what w dot is, it's simply x double dot plus f of x times x dot. Okay, x double dot is obvious. Apply the chain rule here with respect to t. The derivative of f, big F, is little f, and you're left with x dot. And what you can now do is you can make use of this equation to replace this term. Okay, so using the Leonard's equation, you have that w dot is equals to minus g of x. Okay, and x dot is just the definition of what we have there. So you can see this now is a different first order system of the second order system, right? So first order systems associated with a second order system are not unique. There's more than one of them. They have the same answer for x if you get a specific solution, but you have different variables are possible. So there's different ways of making a first order system from a second order system. And the criterion for doing so is to find a first order system that you can actually, that's easiest to analyze. Okay, so what we're now going to do is work out the Nullclines and the vector field. Okay, so exactly as what we've done with analyzing an ordinary system, the first thing we do is the Nullclines are when w dot is equals to 0. Okay, and remember what we said about g, it's an odd function, so therefore it can only, and it's positive if x is positive, so it's only 0 is when x is 0. Okay, so that's our one Nullcline. And the second Nullcline is this thing. It's w equals to f of x. Okay, and now here we have typically our f of x. It can have a wobble down here, but it is simply a function that has a 0 at a, is negative there, is positive there, and is odd about the axis. Okay, and now we can go about knowing what we are given about f and g is we put in our arrows. Okay, so when x is negative, w dot is equals to minus g, which is negative, so this thing is positive, so w increases, and x dot lies above the Nullcline, so it also increases, so that's our arrow. On the Nullcline over here, we have that x dot is equals w0, so x dot equals to basically, so w dot is 0, and x dot is equals to minus f of x, so it's positive. Sorry, is equals, the f of x is 0 as well, so it's equals to w, which is positive. Okay, so it points that way. Over here, you can once again say it's still above the Nullcline, so x is increasing, but g of x is negative because minus g of x is negative, so it's decreasing over there. On this Nullcline, it points down. Over there, it points in this direction, which you can actually just get from symmetry of the functions that are given. Over here, it is increasing over there. Okay, so we can already feel there's a potential of a circulatory motion. Okay, so those are the Nullclines for our Leonard system based on what written in this first order form, based on what we know about the functions. So next we're going to do is write out the Jacobian, and we know that the only fixed point of this thing is at 0, because the only place where g vanishes is at 0, and therefore where x is equals to 0, then w must also be equals to 0. So that's the unique fixed point we have over there. And so we want to work out what the Jacobian is, and the Jacobian of the system is simply let's say x dot is the top line, so is simply d minus df dx, so it's the derivative of big F at 0, d of this thing with respect to w, so that's 1. Down here it's w dot dx, so it's minus g prime of x at 0, and then there's no w component for the w dot equation, so that's 0. So that's our Jacobian. We work out the determinant, which is simply g prime derivative, and we know that because g is an odd function and it's positive after x, this thing is greater than 0, so we know it's not a saddle. We also know that the trace is equals to minus f prime of 0, so that's greater than 0 because of what we know of f prime. And so the trace is positive, so it's an unstable fixed point. Okay, so we have an unstable fixed point at the origin, and the new Leonard theorem proved by constructing a trapping region around the system and applying the Poincare-Bendixson theorem that there's a limit cycle. Okay, so we have the fact that we now have a limit cycle for the system, even though we know very little about the functions of f and g. So it's a very clever argument to do it in general. Okay, so let's look at an example. So the van der Pol oscillator is an example of a Leonard system. It was studied also by this guy, Balthasar van der Pol. He was a Dutch electrical engineer, and he studied oscillators for radios during the Second World War. Okay, so radar developed during the Second World War, and he studied this. There were a lot of regions for the Dutch. I don't know where he was, whether he actually was in the Netherlands or whether he had escaped and tried to help the Brits or the Americans. So I don't know that story. Okay, so just to remind you, this is the equation that we have, where we have x double dot equals to f of x times x dot, which is the nonlinear damping term, plus g of x. Okay, and what we're going to do now is when mu is much bigger than 0, so it's really, really strong damping, we're going to start looking at it as a Leonard system. Okay, so there are two cases in which you can look at this. The one is when mu is small and it's very close to a circle. The other one is mu when it's very big, and at the moment we have no techniques to deal with that, but we will be dealing with that. Okay, so it's a very strongly damped system, and in the xx dot plane, I'm just going to finish the slide and tell you the reason for, or sort of the motivation for why people chose this transformation instead of the ordinary one. So I'm going to look at it in the xx dot plane. Okay, and I'm going to illustrate what the disadvantage is. So let's look at the xx dot plane. Okay, the problem is the limit cycle keeps changing its shape in this plane, and it gets longer and thinner as mu increases. Okay, so I just want to give you an idea of what it does. So for example, suppose we have mu equals to 1/2. Okay, and all I'm doing is now to illustrate why this thing happened. Is I want you to have a look at the shape of the limit cycle. So if mu is equals to 1/5, the limit cycle is almost an egg. If mu is equals to 1/2, it becomes square. If mu equals to 1, it gets that shape. And the way I did this was simply, I started any initial condition, I integrated for a very, very long time, and then I get the result of that thing, which is now, I'm sure, is on my limit cycle, and I integrate that for a shorter time, just that it composes the loop. So that's how these things were plotted. They were actually plotted with the same code that you have. Okay, so if mu equals to 2, it's got our duck shape coming up. Okay, if mu equals to 3, it's got this shape over here. If mu equals to 4, it's becoming more and more distorted. If mu equals to 5, it looks like that. Okay. So what this transformation does, and I'll illustrate it more completely in the next lecture, is it gives you a way of basically making all the limit cycles look the same. Okay, so this is just the introduction for the why we motivate this thing, and this is what the limit cycle looks like if we do the normal linearization that we did. This thing, we'll see what it does. It's a much cleverer way of writing the system, and it allows us to analyze it, which we'll be doing in the next lecture. So thank you very much for now. Sorry for the slide delay, but I hope at least you got